In past classes, we've seen connections between time domain information and frequency domain information. In this class, we're going to be exploring how we can observe some of the stability characteristics of closed-loop systems through the frequency domain analysis, specifically tools like the Bodhi Plot. So what we're going to do is we're going to use a few simple examples to kind of motivate this, and then we'll introduce some terms and then develop a more substantial result that helps us determine stability. So if we look at this, this closed loop feedback system, we know that our closed loop transfer function looks like k times g over 1 plus k times g times r. And so we know that the stability of the closed loop system is going to be determined by the roots of that denominator polynomial. And so those roots are where the values of s, for which 1 plus k times g of s in this case is equal to 0. And so one of the ways that we looked at that was we actually created the root locus, which is a collection of all of the values, the points of s, for which are the roots of this denominator polynomial. And so those start, for k is equal to 0, those start at the open loop poles, at the origin, and 2 at -1. And then they move, and they move as we change the value of k. So as we change the value of k, the values of s that actually are the roots of this denominator polynomial change. And so that's what the root locus is plotting. So it's plotting out these trajectories. And so in this case, as we increase k, these poles come together, and then they branch out in this case. And there are values of k that lead to parts of the root locus crossing into the right half plane. So in particular, there are these 2 points at k is equal to 2 where the root locus crosses the imaginary axis. And those are points of marginal stability. And if we increase k beyond 2, then that leads to unstable closed loop poles. And so now we're going to introduce a way of thinking about that and detecting that using the Bodhi Plot. And so remember that the Bodhi Plot is characterizing values of s that are along the imaginary axis, where s is equal to I omega. So it's only looking at values of s in the complex plane that are on this imaginary axis. And so what we're observing is there are some points, in particular these points at k is equal to 2, where we see the root locus crossing that imaginary axis. And so if we look at specifically the same characteristic, the roots of that denominator polynomial, only at points on the imaginary axis, if there are points that satisfy that, then that means that there are roots of that denominator polynomial that are at this marginal stability point. And so we can find those points, we can find these values right here for which this expression is valid. So again, we're looking for roots of that denominator polynomial when s is purely imaginary. And it's possible those points don't exist if the closed loop system is always stable for all values of k. But in this case, there are values of k that make the closed loop system unstable. And we're going to find those points. And so the criteria for finding those points lies in this equation. And if we rearrange that, we can just see that that also says that the gain k multiplied by the transfer function evaluated at I omega along the imaginary axis is equal to -1. And one way of interpreting that statement is the fact that the magnitude of this quantity is 1, and the phase is a 2 pi multiple of 180. And so what we're saying here is that the magnitude is 1, and the phase is some factor of 2 pi plus 180. And so let's just take a quick diversion to understand why I have this minus sign here. So that minus sign comes from the fact that when we talk about our transfer functions, we usually have polynomials on the bottom and polynomials possibly on the top. And we know that the way that our systems are architected, the order of this polynomial on the bottom is larger than the order of the polynomial on top. It's called a proper transfer function. And so because of that, we have more factors, more poles than we have zeros. And for that reason, our phase is always going to be negative for these proper transfer functions, which represents pretty much all systems that we want to talk about. And so because that phase is always negative, because we have more factors in the denominator than we have in the numerator, that's going to be negative overall. The phase is overall negative. And so the first one of those that we can cross is this minus 180. Okay, so that kind of explains this minus sign. So the phase, if the phase is at minus 180 and the magnitude is 1, then that means that we have points on this imaginary axis that are also on the root locus. So we're finding points that are on the root locus and on the imaginary axis simultaneously. And those mean that those are these marginal stability points. And because we know that increasing the gain leads to unstable systems, we could say that any k that makes a magnitude greater than 1 when the phase is minus 180 means that it's an unstable closed loop system at that point. And if k makes this magnitude less than 1, then that means that it makes an overall stable system. And so when we plot this on the Bodhi plot, just remember that a magnitude of 1 is the same thing as 0 dB. And so if we were to look at the Bodhi plot, what we observe is the fact that when we multiply this quantity by k, then the magnitude is changed by that same value of k. But the phase is actually not changed. So notice the phase here is just essentially comes from this minus sign. So the phase is not changing, but the magnitude is changing. So k multiplying by a different value of k just shifts the magnitude and doesn't shift the phase. So the phase stays the same. So that's why if we were to plot the Bodhi plot for essentially 0.1 times g of I omega, and then also plot 2 times g of I omega, and plot 10 times g of I omega, all of these curves in the phase diagram for Bodhi are all the same. But in the magnitude, it shifts them. And because we're on a decibel plot, that's going to change it. You're going to have to convert that magnitude change in k into dBs. But the idea here is the fact that we're going to look at a point where the phase is at minus 180. So in this case, the phase is at minus 180 at omega is equal to 1. So at omega is equal to 1, we're going to look up here and we're going to see the value of k for which the magnitude is 1. And so in this case, they plot the magnitude here and the decibel here. And so the value when k is equal to 2, the magnitude curve here, the magnitude curve goes straight through magnitude 1 at the same point where the phase is 180. So at this omega is equal to 1, we see that the magnitude curve crosses this magnitude 1 point. And so that's indicating, and it's connecting with the fact that these are these 2 points where the root locus crosses the imaginary axis. Again, because we know that increasing k leads to unstable systems, now we can see that when k is bigger, for example, k is bigger than 2, like in this case, now the magnitude plot is more than 1 at the same value where the phase is 180. And on the flip side, if we have a magnitude gain that's less than this critical gain, 2, so it's now 0.1, now we can see that the magnitude is less than 1. The magnitude is less than 1 at the same value where the phase is at minus 180. So that leads us to consider a rule that says when increasing the gain leads to instability, that the system is stable, the closed loop system is stable if the gain is less than 1 when the phase is at minus 180. And so what's cool about this is that we are determining closed loop stability from purely open loop frequency domain information. So this is just information about G and possibly about a gain K, but that we're inferring characteristics about the closed loop system. And again, the key idea here is the fact that the Bodhi plot provides information that tells us where on the imaginary axis, or if and where, the root locus crosses that imaginary axis. Unfortunately, systems are not always quite that simple. This is an example of a system that has poles in the right half plane, so it's an unstable open loop system. So we have two poles here at +2. And what that means is when k is small, you're going to have poles that are in the right half plane. So for small values of k, you're going to have poles in the closed loop poles in the right half plane. So it's going to be unstable. But then there's a point at which, in this case, again, k is equal to 2, the closed loop poles lie on the imaginary axis. And then after that, when k is greater than 2, now your closed loop poles are in the left half plane, and so the closed loop system is stable. So this is looking at it from the other perspective, where now we start with an unstable system, and increasing the gain leads to stability, which is the opposite direction that we saw before. And so going through that same argument says that now, if increasing the gain leads to stability, then we need to reverse the orientation of this inequality, so that we say a system is closed loop stable if this gain is bigger than 1 when the phase is -180. And so what this is starting to motivate is the fact that we have frequency domain information that's useful, but that we need to know quite a bit, and we need to be careful, especially when we get more complicated systems that we need to deal with. Nonetheless, it's useful to kind of think about these characteristics and to talk about and give names to them. And so that's what we're going to do next. So we talked about stability characteristics being connected to this marginal stability point when the magnitude is 1 or 0 dB, and when the phase is at -180. And so the way that these are going to be stated is they're going to be stated in the quote-unquote typical case, which is where increasing the gain leads to instability. So that's going to be the default for us, but of course we've seen examples where increasing the gain actually leads to stability. So that's the way we're going to state these. So in this case, the gain margin is the amount by which the gain can be increased. So it's how much k can be increased before you reach this marginal stability point. And so I'm going to show you that in a picture on the next slide. It's possible that this is infinite if, for example, the system is always stable, which would be the case where the phase is always above -180. And so, of course, we've been talking about this as looking first at the phase and then observing the stability based on the magnitude, but we could do the opposite. We could also say, okay, find the point where the magnitude is 1 and then look down and see what the phase is. And so the phase margin does that. The phase margin takes a look at the phase plot, and so it says where the value of omega, where the magnitude is 1, take a look and measure the amount by which the phase of g of I omega exceeds -180. So that means how much can you change the phase before you lead to this, again, this marginal instability point. So again, we're going to take a look at this from the perspective of increasing the gain k leads to instability. And so the gain margin is the amount that you can increase before you hit this marginal stability. So marginal stability happens when the phase is -180, so that's where you get this point. That's how you pick out the value of omega that we're looking at. So that's at -180, and then we look up in the magnitude plot and we observe that this is below This is less than the 0 dB line. And so then we observe how much we can increase this, this Bodhi plot, essentially how much, if we were to increase the gain K, this would lead to a Bodhi plot that would look like this. And so in that case, that one is still stable, but there's a value where we increase it so much where it increases and it eventually goes through this point here. And so that's what we're measuring by this gain margin. On the other side, we can look at where the magnitude plot crosses the 0 dB line naturally. That would be this point. So that identifies this frequency value. And then we can look at the phase plot and observe how far we are away from minus 180. Because again, that is the point at which you would reach this neutral point. So remember the multiplication by the gain K does not change the phase plot, but it changes the magnitude plot. And so for that reason, we do measure the phase margin in degrees, but again, keep in mind that if you were to multiply this phase margin, or multiply G by K, this phase plot is not going to change, but this would. And so, but both of these, gain margin and phase margin, are ways of quantifying essentially robustness of stability. So how close you are to stability, how close you are to instability. So in this class, we won't get too deeply into some of the ways in which these particular quantities can be used. However, they are a way to handle model uncertainties. So for example, if you have a part of your system that you have not modeled, this gets at this robustness idea, then your system may change a little bit. In fact, so now you're not shifting this line, but the true line maybe is something around this. And so you would like to make sure that you are far enough away, this gain margin, say, is big enough that even with some small perturbations, you don't change the stability characteristics. So again, this is one thing that we won't get into too much, is this notion of time delays. And so we haven't really talked about a system being time delayed, but this is the idea that the response of a system is not immediate and that it's delayed by some amount of time. And so this phase margin is a way of helping to quantify that. It's related to this, this response delay. And so the ultimate point is the fact that we can visually pick these gain and phase margins out, and this can help us understand stability, again, closed loop stability, from open loop information, and which is an exciting connection to be able to make. The challenging thing is that we need to understand vaguely how this system operates, in the sense that we need to know whether increasing the gain leads to stability or it leads to instability. And there could even be systems where the poles go in and out of the right half plane more than once. And so that becomes very complicated. So in these particularly complicated systems, we're going to include a new characteristic and a new plot that plots our frequency domain information in a different way, and that's the Nyquist plot. And so that's the bulk of what we'll be doing in this class.